Good morning. So, first talk of the day, and I'm going to talk about SQL Server 2014 in-memory OLTP and why is it being upset at me? There, because it's not in memory, that's why. Okay. So this is me, and I got to stop it coming down like that, but this is what I do. This is the company I work with, a company named SQL Skills. If you know SQL Skills, you know Kimberly Tripp or Paul Randall. Probably not me, maybe not. There's their website and blog, and I've written a bunch of stuff on 2014, including how to make one transaction depend upon the other and have them all roll back in Hekaton. Email and Twitter, and there's some stuff I've done. I wish it didn't come out one line at a time. And 2012, I actually wrote a chapter in Kalen Delaney's book on special indexes, which is interesting. Which is interesting to me. I'm sorry. Spatial indexes, full text search indexes, XML indexes, semantic search indexes. Okay, let's go. So this talk is about in-memory online transaction processing, which is also known as Hekaton, which also has another code name that I'll talk about, and we'll be talking about these things. So there's two general categories of applications that live in the database world. One of the main ones is called OLTP, and in OLTP apps, you actually read very few rows at a time. You're usually reading a row about me or about somebody and displaying all the information on the screen. And you usually read many or all of the columns in every row. And in OLAP applications, you usually read a lot of rows. You're doing reporting, or you're doing cubing, or you're doing some kind of analysis, and you read very few columns in every row. Fact tables are huge, 25 columns, and you need maybe 2 of them for any one query. And so in SQL Server 2012, they introduced technology to speed up OLAP apps. And they thought, well, really, though, the majority of our users are OLTP. And so in 2014, they introduced technology to speed up OLTP apps. And this is now called, marketing people got to it, and it's called in-memory OLTP. It was actually codenamed Hekaton, and Hekaton means 100 times. I don't believe they've got an actual user to go 100 times faster yet, but the premise was that the goal was 100 times faster. So they did things like get rid of 99% of the instructions that you would execute if you're running in a compiled stored procedure. And they invented an entire other engine for this thing. It's also known as XTP, Extreme Transaction Processing. And that sounds more markety than anything else. But if you're actually looking to diagnose things, if I go into Control Panel and then go to Administrative Tools and go to, goodness, where is it? Where's perfmon? Perfmon just looks funny at this resolution, that's all. And I go and add a perfmon counter. Do realize that outside of the SQL Server set of counters, there appears the counters for XTP. So do realize that XTP will be useful to you. Or if you want to go into SQL Server Management Studio and look for extended events because you want to trace something that's not working the way you think it is, and you go and make an extended event session, you'll see a bunch of stuff for XTP, and they're all called XTP. So, or most of them are called XTP. So extended event session, new session, call it Z, come on, there. And I want to look at the debug channel. Remember that if you ever want to look at any internals and extended events, you want the debug channel, because that's the one that has all the internal things, and then look for XTP, and you've got a ton of things that you can look at. So XTP is not just a marketing buzzword, it's actually what things are categorized as in the diagnostic tools. Sorry, I do mostly diagnosis. So those are the 3 names for it. So really this feature consists of 4 main features. Actually, 3 of them are features. One is sort of a good thing about it, an implementation detail. And the first feature is there's a brand new storage engine. This guy runs in his own storage engine. They've not using the regular storage engine, they're using his own. These rows don't live in pages and they don't live in extents and anything like that. They're just sort of disembodied rows that live in memory. And this is memory optimized tables. So if you have a memory optimized tables, basically, memory optimized tables are based on linked lists and pointers, not pages and extents. And then we have the compile store procedures. Compile store procedures at this point in history, and do realize it is a version 1 feature, they're going to add things. At this point in history, can only access memory optimized tables. So if you want to join with a memory optimized table and a non-memory optimized table, you can't use these. And these actually have not only a separate procedure compiler, so you can compile stored procedures into assembler, like big deal, right? But they do have a separate query processor, and it works differently than the regular query processor works, and I'll show you a summary of how that works. And then finally, it's lock and latch free. So they have tables that are lock and latch free, they have transactions that are lock and latch free, and they actually have indexes that are lock and latch free. And how do they do lock and latch free? That seems kind of strange. And what they do is they assume that every transaction will commit. And so if things don't commit, you don't wait, but you are eventually going to roll back, and we'll see how that works. And then finally, the big deal is, apparently it's fine to go out and build another database for something. I was reading an article that somebody had spoken to Michael Stonebreaker, the database guru, and he said that we were going to separate databases for separate things, and he mentioned an OLAP column store type database, an in-memory database for OLTP, and array-based database for analysis, like SAS has an array-based database. And the interesting thing is he thought these were all supposed to be different databases. The SQL Server folks think this is all supposed to be built into SQL Server. So a lot of the work they did was actually to integrate it so it shows up as regular tables, the metadata shows up as sys tables, and you can interact between these tables and tables that aren't memory optimized without much problem or without a lot of overhead. So the fact that they're built into SQL Server is an interesting feature as well. Like I said, that's not a feature, an implementation, that's not a feature itself, but that's sort of an implementation detail, but that's a big detail. That means you can change part of your application without changing it all. Anybody is free to contradict me if they want. I'm not an expert in this, but supposedly Oracle times 10 is a separate in-memory database, and you must convert to times 10. You're either in there or you're not in there. With this, you can be half and half. So the components of this are the XTP storage engine, and the XTP storage engine does all of these different things. It manages storage, it manages two types of index. Notice we have hash index and range index, and the range index is actually based on something called the BW tree, which is a lock and latch free version of the B tree. Transactional operations are handled by the storage engine. They have a multi-version concurrency engine, and checkpoint is different for these guys, recovery is different for these guys, and the only thing that's about the same is high availability. So in-memory tables, to me, when I first heard about it, sounds like the system crashed, the table is gone, right? These in-memory tables are transactional, point-in-time recoverable, and persistent. So when they actually write the in-memory table, they will also write to the transaction log. And the transaction log turns out to be the biggest bottleneck at this point, because the transaction log is a synchronous write. So they actually have something for that if you want to be risky. But what they also do, what they also do is persist things in continuous checkpoints. So basically they write continuous checkpoints to files in memory that actually live in file streams, if you remember file streams from 2008. And so they can recover everything with point-in-time recovery. They can also ship those over across to a high availability replica and do high availability with those as well. The things that do not persist in a high availability failover are the things like memory optimized tables that aren't persistent and memory optimized table variables. But if you call a table persistent in the DDL, it will persist. The XTP compiler actually compiles stored procedures into code, and it's assembler code. They use an intermediate format that's XML, but they take table definition and stored procedure definition, and they compile it into an XML format, and they compile that into C, and they compile that into assembler. And I sort of spoke before myself here. They also do this with table definitions. So if you have an in-memory table, it actually produces a DLL as well. And this DLL contains the I/O routines for this table for the new query processor, for the new query execution engine. So native access routines for in-memory objects. And then finally, integration with the rest of SQL Server resources. So integration with transact SQL statements, ordinary transact SQL statements that are not compiled, and a library of functions for compiled procedure, because the compiled procedure has its own function library, or through interop, it can actually use SQL Server's library of functions. There's limitations. So to get started, because most people like to see it, You must have a 64-bit version of SQL Server. It must support a machine instruction called compare and swap. And most 64-bit servers support compare and swap. I think there's one virtual machine vendor that doesn't support it unless you turn it on. So if you're having trouble with it, you're either running the 32-bit edition or you have one of the few 64-bit processors in the world that don't support compare and swap. And compare and swap is one of the ways that they have B-tree-like indexes that are latch and lock free. You need a database with a file group for memory optimized data. It's not good enough to have a file stream file group. You have to have a file group for memory optimized data. It will produce, though, a file stream-like format. And file group can have multiple containers. And the reason why you might want to have multiple containers for your file group is that when SQL Server comes back up again, it actually loads all the memory optimized tables out to memory. And it will parallelize that load. So if you have multiple file groups, then you can load it in parallel to load faster. So the database isn't available until everything gets loaded out into memory. And actually, it is quite fast that you would think, oh, that'll take a long time to come up. Doesn't really. And again, the checkpoint data is stored in file streams. And you want to carefully consider the collation of your database. Because one of the limitations right now is that if you're doing comparisons in compile stored procedures, or if you're writing indexes over character-based columns, you must use a bin2 collation. And if you haven't used bin2 collation, it's a collation based on the Unicode code point number. And what that means in terms of reality is the uppercase characters will all sort before the lowercase characters. So that's the only way they can do a where clause in a compile procedure. Remember, you can use SQL interop, like I said on the last slide. So carefully consider the collation of your database. You can also, for your database, consider memory optimized elevate to snapshot. So the memory optimized tables support 3 transaction isolation levels. None of them are read committed. So the lowest isolation level they support is snapshot. The one after that is repeatable read, and the one after that is serializable. And we'll see if we have time how each of these works. So normally, of course, SQL Server is going to run it read committed. And at first they thought, well, that's okay. We'll make everyone put a snapshot hint on every memory optimized table that they execute in SQL. And it's like, nah, maybe that's not a good idea. So you can run it read committed. Even in a transaction, if you have this turned on, it'll just escalate everything to snapshot. And actually, you'll see why we need snapshot later on. And then you can carefully consider something called delayed durability. So that's another feature in 2014. You can use it outside of Hekaton tables as well. Here's how it works. Remember now we have the transaction log as the bottleneck. So what happens with the transaction log is usually you commit the transaction, they write to the transaction log, and then they get back to you with the information that it's been written. And you sit and wait until they get back to you with the information. So what delayed durability does, and you can do this if you'd like, is you say commit, and it goes to write to the transaction log and starts to see it, find it, knows that it's out there, and then it returns immediately and says it's been committed. And so you have the potential with that delayed durability to lose data if SQL Server crashes or in odd race conditions that happen at shutdown time. So do realize, though, that'll make it run way faster as well. The one that I've seen with the many, many inserts in a row, which is the one everybody likes to do and I refuse to, will actually run 20 times faster if you have delayed durability on. So you can tell that the transaction log is the big bottleneck. Okay, so we need a demo. So I'm trying to cut down on demos because I do have way too many of them. And so the demo that I'd like to do is actually one that's a complete end-to-end demo that you can get. This is the public demo that they've put out for everybody. And this uses AdventureWorks, of course. And so the first thing it does, if you've seen this demo, whoops, sorry. I actually have a bunch of my own demos where we start from scratch, but this sort of has one of everything. So we'll see what we get. Okay. And it's this one right here. So go. By the way, I'm going to give you all of the demos as if I did them all anyway that we have from the 5-hour version. So basically in AdventureWorks 2012, it's going to check to see if you have an in-memory file group, which I don't right now. And if you don't, then it's going to add an in-memory file group. So it's going to add one called AdventureWorks 2012 mod, and it's going to add a file name to that file group. And you'll see that it'll produce something that looks exactly like a file stream file group. Sorry, file stream file group. There we go. And so if I go up to my T drive, we should see that the in-memory data, and if I wait long enough, is going to be stored right here. And notice this is a file stream file group. Sorry, let me go back and zoom it on. This thing looks so hideously large in this font that it's like I forgot about zoom it. Good. So anyway, if we go back to the file system, there we go. And we can see that under data, it's over here. And basically, there's the file stream concept with the multiple GUIDs, first one, and then the first one under the first one. And right now, it's empty. This is going to be filled in later on. Yes, ma'am? No? OK. This is going to be filled in later on with a set of checkpoint files. Checkpoint files are basically pairs of files. And the big one is where they store the data. It's a 128 megabyte file, and there's 8 of these pairs. So basically doing this is eventually going to allocate a gigabyte of space just to put a memory optimized file group on there. And then the little ones are actually delta files, which is where they store the key values of the rows that have been deleted. And we'll see that this is necessary for the multi-version concurrency control. So usually if you wait long enough, these appear, but we'll forgo them for now. We'll see them later on. So notice that at this point, you can alter the database to set memory optimized elevate to snapshot, which is easy if you don't want to have a hint on every query that runs in read committed. And then a couple of other set options, which I'm not sure that we need because I did it yesterday without them, but we'll go. And then they've basically taken something that looks like some of the tables in AdventureWorks and actually made them in memory. So here's a table, sales order header in memory. And basically, this is a sales order header, sales order detail. They have one for in memory and one for on disk. And then you have a stored procedure that can actually insert these things and one that can update them just to take more time so you can see the difference more easily. Basically, they just took a subset of columns. And you might notice that these have to have a primary key. The durable tables have to have a primary key. The non-durable tables just have to have an index of some kind. And we'll see the reason they have to have the index is just to tie all the rows together. So this is going to have a primary key, non-clustered, because there is no such thing as a clustered index in this world. No such thing. So a non-clustered primary key that's a hash index, and then you have to tell it how many hash buckets you want. Now, right now, this must be hard-coded, and to change the number of hash buckets, you actually have to drop the table and recreate it. And at this point, it's just going to have a default of new ID. That's OK, too. And by the way, everybody's told forever that it's not a good idea to use a GUID as a primary key because it's going to cause fragmentation. But in this storage engine, it's actually not bad at all because it doesn't work in pages and extents, and so you don't care about fragmentation. There is no fragmentation. Everything's scattered hither and yon. So, I don't think I need that many rows. And the premise for this is, the premise for this is 2 times the number of rows you expect to have. Now, if this is a fairly heavily executing OLTP system, how many do you expect to have at any given time? Just remember that you do have to drop the table to change this. And this does not mean that you're limited to that many rows. All it means is that if you don't allocate enough hash bucket, your hash chains will be bigger and it will slow down the access to them. So, yes, sir? Can you customize the hash function? No. They actually have a built-in hash function that they have that's customized to the exact number of hash buckets that you have. But no, they do. That's internal. Yeah. OK, so we'll do that. And there's maybe a couple things that they've gotten rid of. In this world right now, there are no check constraints. The only constraint that you can have is a non-null constraint. And I believe you can have a default, too, right? There's a default constraint. No check constraints, though, and no foreign key constraints, and no triggers. So the way that you fake a trigger, of course, is to write a stored procedure with an insert statement in the middle. And then after the insert statement, because SQL Server supports after triggers, right? After the statement, you can see what you've inserted and roll back if you don't want to. There's nothing really instead of triggers. And for foreign key constraints, you just do without for this point. They actually have some code in the books online about how to fake a foreign key constraint. Remember, this is version 1. And if you want to see how far they can get in a version, Remember that Column Store 2012 was version 1. Column Store 2014 is version 2, and it's almost done. Right? In fact, they're looking for little rough edges to smooth out, but it's almost done. So we got a table over here. Anything else that's interesting in this? We should have, he said, there's another table. And this one actually creates that's a hash index too. You can have up to 8 indexes in a particular table, and you can have hash indexes or range indexes. And I was trying to find you a range index because you've seen all these before. You can also have memory optimized table variables because the compiled store procedures cannot access any any non-memory optimized tables. Did I say real? Non-memory optimized tables. And tables in tempdb are not memory optimized. So you are left with, memory optimized table variables, which will replace temporary tables in our mythology. Okay, so there's a memory optimized table variable here, but there we go. So to create a memory optimized table variable, you must create a table type. It must be a strongly typed table. And you create the type, and it must have an index, but it doesn't necessarily need to have a primary key because it's not persistent. Notice that in the other ones, we've already seen memory optimized equals on, and schema and data is the default, so that you will actually, they don't call this out explicitly, but memory optimized with schema and data is the default. For table variables, of course, you're not going to persist the data if the system crashes. And so therefore, it's not by default going to be persistent. So let's just drop these and create them. Does anybody have any questions about this so far? Up to 8 indexes per table. And I'll just get to this far so we can do the stored procedures later. Goodness, he said. That's right, scroll in front of everybody first thing in the morning. There we go. So there we have it. Okay, and we'll put these out here. Okay. So I wanted to show you how this exactly looks, and I'm sorry, but I'm going to have to skip through a couple slides, and I'm going to go back to them. There we go. And so this is how the table is actually laid out in memory. This is how the rows is laid out in memory. And notice that they are not laid out in pages. They're linked lists over hash buckets. So this is a hash index on name, hash index on city. Every row contains a begin timestamp and an end timestamp. And there's the begin and end timestamp. You can have up to 8 indexes, but indexes are pointer based because really they're pointers to memory locations, which is where the rows live. So in this case, it looks like he's got 2 indexes, and then the rest of the data comes after this. So as not, I believe, so as not to change everything in the system, right now these are still limited to 8060 byte rows, just so I believe they won't have to change everything that says 8060 bytes with an if statement that says if it's not memory optimized tables. Now, what you have here is a hash index on name, and supposedly the hash function in this case, which they faked, right? You can't actually put in your own hash function, but we're pretending you could, is actually going to hash based on the first letter of an alphabetic name. So basically, I would have 26 hash buckets if that was the case, unless I wanted to support accented characters or different characters. And so notice that every row has a begin and an end timestamp. You always read as of the beginning of your transaction, which is why snapshot is the lowest isolation level. So in this case, what have we done? Well, it looks like at transaction ID number 50, actually this is a timestamp, not a transaction ID, but at timestamp number 50, we've actually inserted a row Jane from Prague. And Jane from Prague actually has a pointer to this index, from this index to her, and a pointer from this index to her. And notice that that row is good forever. We haven't changed that row yet. However, right over here, we actually have inserted a row from John in Paris, and we inserted him at timestamp 100, and at 200, we actually updated him, and he moved to Beijing. So basically, when you insert new rows, they insert from the current timestamp to infinity, and when you update or delete a row, basically what you do is just go back and change the end timestamp. Notice John is still there, so that's fine. And John's still in the database regardless of what number you're at. Susan apparently has been added and deleted. So she was added at 90 and deleted at 150. So imagine, and notice that these are all controlled by hash buckets. And even though Susan's deleted, she's still in the system because there must be somebody that has a current transaction ID between 90 and 150, or at least less than 150. Once it gets to the point where nobody has a current transaction ID or timestamp less than 150, then Susan disappears, and she's actually collected by a garbage collector. Remember that they did actually put that row out to the checkpoint files and to the transaction logs, so you could still recover it if you had to, point-in-time recovery. Everybody okay with this? So if I read at number 110, who do I get? Well, I get John in Paris, and I get Jane in Prague, and I got Susan. And if I read at 214, time 214, what do I get? Well, I get John in Beijing and Jane in Prague. And so the idea is these are multiple versions, multi-version concurrency control, and basically you read as of your begin timestamp. Everybody okay with that? Okay. And notice these are basically done, one more time, with linked list over hash tables. Singly linked list. Here's the hash table for the letter, goodness, its last name, J. So here's the linked list for J, and we go here, and then to here, and then to here. And basically, when a row gets deleted and is gone for good because we have somebody past that number, we don't have anybody before this number 150, then what happens is the garbage collector will actually kick in, and garbage can actually be collected, or linked lists can be unlinked by the person who's doing the select, which I think is interesting. If you're doing a select and the garbage collector has told you that this is okay to delete, then you can actually unlink this chain and link it to the next person instead. So it's a cooperative garbage collection system where some of the garbage collection is actually being done by the readers, which is intriguing. Everybody okay with that? So we'll go back a couple slides, and then we'll do some demos. So the storage, I talked about the storage before. They're called checkpoint file pairs. Each checkpoint file pair is one data file and one delta file, and they should be out there by now. So I'm a Rumpelstiltskin type person. I like to see things, and if I can see them, then I know they're real. And if I can't see them, then I'm confused. So here's our checkpoint files right here. There's a bunch of them. Notice they have these weird file stream names, but we don't care. The only one who's going to talk to them is SQL Server. And notice that the data is actually going to be stored in these files. Notice they're pre-allocated. And the deleted row keys are actually going to be stored in those files. And we're allocated to start with 8 pairs, and that would mean about 1 gigabyte of storage. So your first backup might be a little bigger than you might expect. And in the RTM version, this is CTP2, and I only have 2 and in the RTM version deals. But in the RTM version, if you have less than 16 gigabytes of total storage, these will only be 16 megabytes large. They won't be 128. So I won't waste not waste, but I won't take up a gigabyte of memory every time I allocate one of these. Now, we defined some tables and a table variable. And so those got actually compiled into a set of I/O routines. So we can look and see where those I/O routines are, those DLLs of I/O routines. Now, the easy place to look is in, sysdm OS loaded modules. And we can see that they're there. But they actually live outside of SQL Server, under SQL Server, version of SQL Server, MS SQL, under data. There's a directory called XTP. Remember I said the key to everything is to realize that it's called XTP? And under XTP, there's a subdirectory for each database that has memory optimized file group. And ours is, I think, 13. No, not 13. You can tell. Ours must be 6. AdventureWorks, there we go. And there's a bunch that start with, that have a T in between. Those are for tables. So XTPT, and the one for the table variable is called XTPV. So that's fairly useless information except to know that they exist, and that's where the I/O routines are. And if you want to read their C code, you can read their C code if you'd like. It's C code generated by a code generator, and so it's basically a jump table with a lot of go-tos in it. And this is so things will go fast. So now we have our checkpoint file pairs, and the checkpoint file pairs, though, we never go into the data file and delete rows. If you insert a row and then you delete a row, you basically have the row in the data file and its key in the delta file. Memory optimized tables. Table variables must be strongly typed. That was fairly obvious. Durable and non-durable tables. That's in the create table statement. And the durable tables are persisted into the file stream like file group at checkpoint. Durable tables are reloaded at startup time. I'm repeating myself here. You must have enough memory to load these tables in at startup time. So if you take a backup of the database and move it to something with not enough memory, that database won't come online. So you do have to have enough memory. There's nothing about the backup that tells you how much you need either right now. Non-durable tables are not persisted or logged, and so one of the usages for them is ETL. By the way, table variables, memory optimized table variables, can be used perfectly well with regular transact SQL for anything you might want. Right? They're not tied to this system. It's integrated. So the memory optimized tables memory is non-pageable because they are actually pointers to location, memory locations in memory. And it's a different memory clerk than the buffer pool, but it is covered by max server memory. So do realize that when you put these things in memory, you're taking that memory away from the buffer pool. There's an approximate 80% hard limit that they can use for memory optimized tables. What do you mean approximately 80% hard limit? Well, it depends on the total amount of memory in your system, and it varies from 70% to 90%. The more memory you have, the bigger percentage you can use. You can also limit the memory for these tables with the resource governor, and basically what you do is make up a resource pool, and then you install your database into it. I have a demo of that. Maybe it's interesting, maybe it's not. Yeah, now that you said that, it has to be interesting, right? Else you wouldn't have dithered about it. Okay, so here's the way. You can't do this, you can't pre-put something in a buffer pool. You can't put a database in there that doesn't exist. And so what you have to do is take the database offline, do this and bring it back online, or you can do this with a restore with no recovery as well. So this is goodness, right here, a restore with no recovery. You restore with no recovery from a backup, and then you create a resource pool for Hekaton tables, and with a max of 50%. Now that's 50% of the memory in the system. 80% of that 50% is what you get for memory optimized tables. And you can share these pools with multiple databases. And then basically what you do when it's offline is say execute XTP bind DB resource pool. And you bind your database to the pool, and then you bring it back online. This brings it back online by restoring it with recovery. Everybody okay with that? So you can limit how much this is going to take. And we already said it's based on linked list over hash buckets. Fine. So it uses a multi-version engine. You've seen this. Inserts are inserts into memory with with an end timestamp of infinity. Updates are an insert and a delete. And deletes are close out the end timestamp. Put your ID in the end timestamp. And row access is based upon the statement begin time or the transaction begin time. So you always see everything as of the beginning of a statement or the beginning of a transaction. And isn't that the definition of snapshot isolation? Yes, it is, right? You will see as of the beginning of the transaction or statement whether or not things change during that. So the reason I make a big deal of this is the books online says you can do read committed, but it's not real read committed like SQL Server does, it's snapshot. All rows are garbage collected, old rows when they're no longer needed. And basically what normally happens is the readers will actually unlink the rows that are not needed. But remember, they're reading through one set of pointers, right? One linked list. So they can only use the linked list that they're actually using at the time, the index that they're using at the time. Suppose I have 3 indexes. I can unlink one linked list. But if I have indexes that aren't used, those will never get unlinked. So what happens is the garbage collector will actually have to take care of them themselves. And this is colorfully enough called dusty corner garbage collection. Right, they go into the dusty corners and find all the ones that are deleted and unlink those. There's at least 2 performance monitor counters for dusty corner garbage collection.
So what happens if you update a row that's been deleted since you've read it?
Your transaction rolls back. Yeah, and we'll see that transactions can roll back immediately, or transactions can roll back when you say commit. Which is an odd thing to me, that they'll let you go forward until you say commit, and then they'll say, nope, too bad. Right? The premise of it running fast is that all transactions will commit. But if you were actually trying to update a row that's been deleted already by somebody else, then it would roll back immediately. Same thing if you try and update a row that somebody else has updated since the beginning of your transaction, it'll roll back immediately, just like Snapshot does in SQL Server. Everybody okay so far? Good. So there's a DLL created, and we really saw this stuff, right? We can do slide, 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 but seeing it is just as good. And we could look with SysDMOS loaded modules as well, and we'll see at least, 12 of them, because how come? Well, I had about 7 that I created. So when I create, they'll load the module in automatically. I also had another database out there. So when SQL Server came up, what happened is they recompile all the DLLs. They don't drop them when it comes down, but they recompile them when it comes up to make sure they're not stale. And then they use those DLLs to load the data from the checkpoint files out to the memory. So you'll see a lot of them if we do it now. Okay. So indexing. 2 types of indexes, hash indexes and range indexes. Hash index is only good for 2 things. It's good for an equality predicate, sorry, 3 things, I guess. It's good for an equality predicate. So if you have an equals predicate, it'll use the hash index. And if you have an in clause, which is basically multiple equality predicates, it will use the hash index. Otherwise, the hash index does a scan. That's the only thing that it does. Okay. You can have up to 8 indexes, I said that. Tables must have at least 1 index because that's what ties the rows together, right? If you don't have index, it doesn't know which rows belong to which tables. And durable tables actually need a primary key. That's because the primary key is persisted to the Delta files if you delete rows. Indexes must be declared at create table time. There is no create index, there is no alter index, and there is no alter table. And for hash indexes, fragmentation and fill factor do not apply. And for range indexes, we'll see that they apply very little. Everybody okay with this so far? So if you're a DBA that does a lot of index rebuilds, there's no alter index, right? Your index will get rebuilt if you really want to, if you bring the system down and back up again, or bring the database offline and back on again. But with a hash index, you don't really have to rebuild the hash index, right? And so fragmentation and fill factor are not really an issue. Indexes are not stored on disk at all, right? They're not persisted at all. So that's another place where they gain speed. What happens? Well, when you load the things in after SQL Server comes up, it makes up the index. And as you insert, delete, and update rows, it maintains the index. And that's basically how it works. So there is no storage of index data at all. And by the way, if you come to think of it, everybody knows the concept of a covering index? What's a covering index? Somebody tell me. Nobody, huh? This is the audience participation part, you know, and I know everybody knows what a covering index is, but anyway. Sorry?
The columns that you actually want to do query,
Mm-hmm.
if you're included in the index itself,
Mm-hmm.
you go to more than book lookup.
Correct, yeah, except that's one way of putting it. There's always different ways of putting it. So the clustered index is the ultimate covering index, right? The clustered index contains all the columns, and so if you do a select star for it, it covers the select star from. However, sometimes you might want to have non-clustered indexes. In SQL Server, I'm not talking about in memory. In SQL Server, sometimes you might want to have non-clustered indexes. And if you come to think about it, I always think about it this way, everybody gets upset. Non-clustered indexes are really tables with a subset of columns. And the pointer back to the clustering key. And if you don't have a clustering key, then you have a pointer back to what's called a row ID, right? That's really what a non-clustered index is. And so in order to make non-clustered indexes useful, although they are useful for other reasons, it might be nice to have a non-clustered index that contains all the columns you want to read. So if I have 9 columns and I only want to read 3 of them, if I have a non-clustered index with those 3, then that's called a covering index, all the columns I want to read. Well, if you look at this system, pretty much because they're all pointer-based, every index is a covering index. None of these index ever point to anything except for the entire table. So you don't have to have any big deal about covering indexes, and you only have 1 copy of the data at all. Of course, there can be multiple versions of it, but you have 1 copy of it. Okay. There you go. That means also you don't have to keep track of updating the indexes except to update the pointers.
Can indexes be on multiple columns?
Yes, they can. However, in a hash index, that's less than useful, right? Because they do point lookups, and so basically both of the values have to match for them to be able to use that with hash indexes. Normally, if you want a multi-column one, you want a range index. All indexes are covering. Fine. Okay. Well, I can do this without slides, right? So equality or in predicates, I'm like way ahead of my slides. And the number of hash buckets must be declared with the table. If you want to tell how much memory that takes, that's an 8-byte pointer, and you should expect 2 times the expected number of rows. Now again, if you don't allocate enough hash buckets, how are we doing for time? If we don't allocate enough hash buckets, what happens is things will hash to the same bucket, and it's not that you'll run out of space to put your rows, is that these linked lists will be longer, right? Because and they will have to read through the entire linked list to be able to see one row. Okay, come on, forward. Okay, this is internally rounded to the next power of 2, and there's a hard list of over 1 million hash buckets. Billion? 1 billion hash buckets, okay. And hash collisions chain rows and decrease performance, I just said that. And so you would increase the bucket count. How do you increase the bucket count? Drop and recreate the table. Now, I just saw a video by a guy from Microsoft Research who participated in this. And so one of his big claims to fame was that he invented the ever-expanding, dynamically sized hash table. And I thought to myself, well, you participated in this, why don't we have one here? Right? Seems like that's the next thing he should put in. So it's less useful for composite keys because all the key must match. See, if you ask the right questions, then I don't even have to have slides. Okay. The other type of index is a range index. And this is a normal, I'm squeaking here. This is a normal B-tree index, except that it is latch and lock free. And it's a B-tree index that's called a BW tree index. And if you read the academic white paper that they put out, BW stands for buzzword, because they basically wanted it to do all the buzzwordy things that you could possibly have. Lock-free and latch-free and self-maintaining and multi-versioning, and so they called it buzzword tree. Basically, range indexes are unidirectional. And so if you have an index in descending order, they're not going to do backward scans. So the order does make a difference. And pages are stored differently. These guys are stored in pages, but basically only the, oh, I have a board. Basically only the pages are stored. They don't contain copies of the data. So if this is a B tree, oh, you had to use red, didn't you? Okay, this is a B tree. And normally, if you go down enough layers, these things down at the bottom are called root pages. And usually in a B tree, the root pages actually contain a copy of the columns in the B tree, right? They contain the data. Well, these B trees don't contain the data in their root pages. What they actually contain is the pointers. So there. So that's a BW tree done with pointers. Now, how did it get to be lock and latch free? Well, this is where we need our compare and swap instruction. So basically, we're maintaining the pointer pages up here that point down to the root pages at the bottom, and we're maintaining our pointer chains here. So what happens is, as index pages are updated, they're replaced with new pages. Actually, they're replaced with deltas as well. So you might have new pages, but you also might have information in new pages that says, this is the difference between the way the page is now and the page was. And what they do to make it lock and latch free is to add a level of indirection here that are pointers to all of the pages. So basically what happens is if the pages change, they'll either record the delta or put out new pages, and they basically just change the pointers. And they change the pointers to point to the new information, amazingly, with the compare and swap instruction. And a compare and swap instruction is an instruction in assembler, of course, that actually does this in a transactional manner, consistent manner. It's either this or it's that. And so therefore, they don't need any locks or latches in order to maintain this structure. It is a mostly different structure than the regular B tree, however. Everybody okay with that? That's a real quick summary of that. But it's lock and latch free and everything else. It just doesn't support backward scans. And it does support composite keys properly, of course, but the leading key column is always like everything else is. Okay, so we got our tables, we got our table variables, and now we're gonna do compiled procedures. How am I doing here for time? So this was 11:30, 12:30, 1 o'clock, okay, good. All right, so these are written in Transact SQL. In fact, you cannot touch these with CLR, so it's not a concept that's like CLR. And the Transact SQL is translated to C code via an intermediate thing that's XML. You can see the XML, and a native DLL is produced. Now, unlike the tables that are produced at system startup, the DLLs are reproduced at system startup. because they have to load the tables at system startup, and so they have to recompile the DLLs. When the system shuts down and starts back up again, these DLLs are recompiled the first time that you use them. So there's a little hit the first time that you use them. And the query plan, and actually it's a hard-coded query plan, is created at create procedure time. Basically what they do is they figure out between query plans what's the best query plan for what they have, and then they hard-code it into the stored procedure. And what do they use to hard-code it? They use the I/O routines and the subset of iterators or operators, query iterators or query operators that they support, and they basically hard-code the plan. And that means that they're also not going to go back and update the plan. That also means that at the time that you compile the compiled stored procedure, your statistics better be up to date, one, if you wanted to choose between different join strategies or query strategies. Actually, they only support one join strategy, which is intriguing. They only support right now nested loops join strategy. But having said that, they do support a subset of iterators. And that also means that there is no automatic statistics update for memory optimized tables. If you want the statistics updated, you update them by hand, which means the database administrators that now have less to do because they don't have to reorganize indexes or rebuild them, now can figure out when to schedule the manual statistics update, because there is no automatic statistics update. And that would have to be scheduled right before you want to compile the compile stored procedures. And for people that are concerned about the lack of parameter sniffing, right, everybody's heard about parameter sniffing in stored procedures. Basically what they do is use the statistics. If I have a parameterized query in a stored procedure, select star from authors where age is greater than some age, when they compile the stored procedure, they actually use the first value passed in to figure out what the plan should look like. That's called parameter sniffing. They sniff the value of the parameter. And since that plan is cached, this is regular SQL, this isn't anything new, because the plan is cached, you can pass in a radically different parameter value later on, and they won't change the plan. So what about those people that depend on parameter sniffing? Remember, it's gotten a bad name recently, but parameter sniffing was supposed to be and is a feature. So if you depend on the fact that they know the value that's passed in at compile time, what you can use is the optimize for query hint. So option optimize for parameter name equals parameter value. So you can actually pick what parameter value this is supposed to be optimized for. Everybody okay with that? Good. The Books Online, by the way, has a list of hints that aren't that are supported, and they can put that in there. So do realize it's perfectly well supported. We did it yesterday. And there's no alter procedure. So if you actually want to get a different plan, you have to drop and recreate it. And there's no create with recompile, there's no SP recompile, there's no nothing, right? It's hard-coded. Okay. And they can only access memory optimized tables right now, no joins between memory optimized and regular tables. And compiled code with a new query processor is generated for memory optimized tables. Yes, sir?
This looks pretty much glossy. Can we tweak those C files to, let's say, do these joins?
No. Can't touch the C files. Right? They'll recompile over top of them if you touch them. And they're in a directory that the only person that has access to them is the SQL Server service account and the OS administrator, mostly because they can't get rid of the OS administrator. Right? So yeah, you can't touch those. I mean, you could try, but the next time it's going to actually write over your stuff, and so yep, there's no point in trying. Yep. Everybody okay with that so far, with the I/O routines and all that good stuff? Okay, so we now have a different query processor, and if we take just a normal SQL query, just to see how it works, I can sort of wave my hands and show you how the new way works. And by the way, remember this way, the new way, only works if you're using compiled stored procedures. If you're using memory optimized tables through interop in the SQL statements, that's not going to work the same way. That's going to use the SQL query processor. Only with compiled stored procedures will they use the new one. So let's just pick a query at random, he said. Let's see, I have this one. Nope, sorry. I have this one from yesterday. Come on. And here's a plan for a query from yesterday. It's a bitmap filter plan. It's rather complex, but that's okay. So the way the query processor in SQL Server normally works is they go to the iterator on the left or the operator on the left, and all of these iterators or operators are COM components. And basically, they have two methods. I forget the exact names of them. One's the equivalent of get me a row and give me a row. So basically, the way the query processor works is to go to this one and say, get me a row. And he doesn't have any rows, so he goes to the one next to him and says, give me a row. And of course, it can go all the way down until somebody's able to give up rows. The ones, of course, that give up rows are scans and seeks. And so eventually, he's going to get to here, that's doing an index scan, and it's going to give a row to the person next to him. Now, some of these iterators are what's called stop-and-go iterators. You do have to stop in the middle and read all the rows. But if the iterators are what's called streamed iterators, you're processing that exact way, one row at a time. So go to the one next to me and say, give me a row, give me a row, give me a row. If it's a nested loop join, we'll do the join with the other table, who's also got to get a row from somewhere. And then we'll go all the way through the query plan for the first row. And then we'll go ahead and do that for the second row and the third row. And so that seems like a lot of extra overhead, a lot of extra instructions. What's nice about that is the query processor, the way it works, is fairly flexible in what it can do. And it can also use things like hash matches that require all the rows before they can do anything, right? So it doesn't go one at a time for everybody. The canonical example of one of these, by the way, is a sort. Obviously, you can't sort the rows until you have them all, right? You can't give me the first row until all the rows are sorted. So there you go. Get rid of 99% of the instructions. What they decided to do was start at the right-hand side and start doing things without this, go to the next one, go to the next one, and actually process them right to left in using the hard-coded IO routines that they actually have. That would get rid of a lot of overhead in asking everybody for a row all the way across. And so with the compiled store procedure query processor, that's exactly what they do. They use the IO routines, they have a hard-coded plan, they don't do this, get me another one, get me another one, and they will produce a query plan for you. You could conceivably see it, but on the other hand, it's all going to be streamed iterators at this point in time, and except for sort, I take it back, except for sort and top sort. And it's a whole different way of doing queries that gets rid of 99% of the instructions. Everybody okay with this? They figured Hekaton, 100 times. If we got rid of 99% of the instructions, we're good. So here we go. So I'll go back to my demo, and we'll actually create the store procedures, and we'll do what everybody likes to see, I guess, which if you like to see it, that's good too. And what everybody likes to see is how fast it can go compared to store procedures that don't use Hekaton. So we're going to insert some rows into these tables, and that's not going to, we're just priming the tables. And then initialize some sequences here for sales. And insert some more, there we go. So once we've inserted all our rows, that's a good time to update the statistics for the memory optimized tables. In fact, for all that, well, that's the only ones that can be in the compile store procedures. So it's a good time to update the statistics before we build our store procedures. So we're going to update statistics. By the way, update statistics in this world only works with full scan. You can't do, sampling. And you update statistics with no recompute because they didn't even want to give you the impression that it was going to make up new plans, right? So you're updating them full scan with no recompute. Okay, so I think we only have two. There's a memory optimized table variable as well. Nope, there's three of them. Okay, so we'll go ahead and do that. And then we'll create a compile store procedure. Now, before we even get to it from the slides, I want to show you what a compile store procedure looks like. The first part looks like a regular store procedure, except that in a compile store procedure, you can actually put a nullability constraint on the individual parameters. That's not possible in SQL before this, and it's not possible unless you have a compile procedures. So you can basically say that these are nullable or non-nullable, and they'll check. After you do that, this has to have a bunch of special clauses. And the premise of the special clauses is the procedure execution will not change regardless of who's using the procedure. And it also knows what its transaction isolation level is before it starts. So the native compilation is basically just saying you're doing native compilation. We'll bypass schema binding for a bit. Execute as owner because we don't want it to execute differently. And the default in SQL Server is to execute as the caller of the store procedure. Now, technically, I believe you can execute as caller, but they're working on that. So execute as owner. You also have a choice of owner, self, or user equals some username. Begin atomic. So a Compile store procedure is an atomic block. And that means that it either rolls back as a unit or commits as a unit. Now, what if you're called from somebody and you already have a transaction? So if I already have a transaction and I'm called from the outside world, they'll actually use something called named save points here. And at the beginning, they will actually start a named save point. And if they have to roll back, they will only roll back to the named save point. Of course, do realize with named save points, you can't commit the inner part of the transaction. These are not autonomous transactions, they're just using named save points. But this is okay in this world because one of the requirements right now is from a compile store procedure, you cannot call another procedure. So therefore, there's nothing inner to roll back if you commit something. Okay. So begin atomic, transaction isolation level you have to name 2, language you have to name 2, right? And you can also name things like date format and date first. You can also, on a per procedure basis, tell it to use delayed durability, unless you have said that delayed durability is not available at your database level. So you can do this on a procedure by procedure basis. Now what about schema binding? Everybody's heard about schema binding? Let me give you a really quick schema binding example that's based on views, which is what you usually see with schema binding, or user-defined functions. Stored procedures, regular stored procedures, cannot be defined with schema binding in SQL Server. So suppose I create a table, and we'll call this table because I think I have T1, T11, and it's going to have the smallest number of characters I can type there. So now we have a table in there, and we have a view that actually refers to that table as select star from T11. Okay, so there's a view. So the question at this point is, I'm executing the view nicely as I go. Never mind the fact that I'm using star for everything. That's all right. Right, select star from V11. Okay, and I'm executing the view, and one day somebody comes in and decides to drop the table. Can they drop the table and ruin my view? And the answer is yes, of course they can. So it's executing just fine until somebody comes and drops the table, and then it just stops working for no good, well, for some good reason. Somebody dropped the table. There we go. So now this fails when I least expect it. So schema binding is supposed to prevent that. Schema binding is supposed to prevent changing any of the objects that that procedure or view refers to, and also changing the data type of any of the columns that that schema or view refers to. So let's just define this again. We'll drop the view and start over again. And we'll define that view with schema binding. So there as, and between the as we'll put with schema binding. And we'll see that that doesn't work the way that it's written right now. So there we have a table. Okay, and there we have a view. And when I try and define the view, it says select star is not allowed in schema bound objects. So no select star in your stored procedures. They want to know which columns to protect the data type of. You can conceivably alter the table and drop a column, unless it's a memory optimized table, and they would be okay with that if it wasn't one of the columns in their list. So we'll put the column in. And then we'll get another error, which says all names have to be two-part names. And the reason why all names have to be two-part names is I could have a bob.t11 and a mary.t11 and a dbo.t11, and they don't want that to change because this is supposed to be bound to the exact database schema that we have right now. So then we'll have to put dbo.t11. So of course, those are some of the rules of schema binding, and then this works, right? And I can select from the view with a star, right? That's okay. But there's no way for somebody to drop a table. People consider schema binding to be a pain, and the reason why they do is because you have to add and drop things into in the correct order based on your dependencies. On the other hand, schema binding means things will never break because things are missing. Everybody okay with that? Okay, great. So it has to be defined with schema binding as well. So did we create these procedures yet? No, this is supposed to be the cool, demo of the whole thing. So we'll create these procedures, and I'll tell you what they do as we go on. And I had an error in one of these procedures yesterday, but it still worked. So we'll create a bunch of stored procedures. All right, there we go. And they pretty much all look the same. They do have, he said, there we go, and we have a seed table to have it seeded with ordered details. And we can fill up that seed table, and let's just stop right there. Okay, so let's see if we can get that far. Okay, yeah, it was cannot execute as database principal because the principal DBO does not exist. This is the most common mistake people make with this demo, and I think they fixed the demo since then. If you attach the AdventureWorks database to the database, or the instance, what happens is, so we'll view the Object Explorer. If the database was actually made up and owned by somebody that's a Windows login that doesn't exist on your system, then it just nulls out the DBO. And so what it's saying is the DBO does not exist, and indeed he or she doesn't, because the DBO is actually empty. So if we go here, notice that the owner is empty, and so it was probably owned by somebody that was an integrated login on a system we don't have access to right now. And so we'll change that. And we'll also change the options to 120, although I don't really believe that's necessary. I do that because I always do the cardinality estimate demo after this one, so. Okay, and cardinality estimate matters. So now that we've done that, we'll try it again. And do you finish there? I hate to oh no, of course. There we go. And we'll try the whole thing again, and it'll be better this time. And remember, we're compiling VLLs at this point, and there we go. So now we have system. And what I'm going to do is there's a sort of stored procedure that calls other stored procedures called insert sales orders. And basically you have the choice of either use memory or not, use in memory or not use in memory. You tell it how many orders you want to put in. I'm going to put in actually 50,000, mostly because it takes about 20 seconds if you put in 100,000 on my machine. And then include update. So basically there's a set of stored procedures, and if you're running in memory, you call the in-memory version of insert orders, and it will insert the orders and insert the order details. It actually inserts the order details from a memory optimized table variable, so it's going to be quick. And if you call it without memory optimized, then it'll do the same set of things for the on-disk tables. Now in addition, this include update actually calls another memory optimized stored procedure or not, just to do more things so you can see that it executes quicker. And basically it'll do 2 updates, I think one for the shipping, one for the billing or something, on the rows you've already put in. And it inserts a variable number of order details later on. As we insert. The only thing you have to be careful about is that you are doing things in memory and you are using compiled stored procedures. So some of the stored procedures are compiled, but the ones that have to call other stored procedures cannot be compiled. Everybody okay? Just the ones at the end of the chain. So we'll do this, which is the demo everybody always likes to see how much better this is. First, we have to actually create that stored procedure. Obviously, this can't be a memory optimized stored procedure because it's calling other stored procedures. It's a driver. So we'll do that. And then I don't think I need this demo reset table. In fact, I think it gave me problems yesterday, but that's okay. We'll put it in anyways, and if it gives me problems, we'll just forget about it. Okay, great. And then we'll initialize the seed table that's actually there to give out order details. And now we're ready to go. Okay. So this is actually going to use the in-memory database, and it's going to insert, let's make it insert 50,000 rows, so we can actually maybe see some cleanup on the checkpoint files later on. And we'll do that. And you can see that it says here, use 7 seconds, then 4 seconds. That's after I bounce my database too. So the storage procedure will have to compile the first time. But remember, that was with 10,000 rows, and I'm doing 50,000 now. So we're up to, see at the bottom, 12 seconds, 13, 14 seconds. Maybe it should have stayed with 10,000 rows. Okay. Come on. It's fairly quick. And the only thing that's sort of disconcerting about this demo, so I have, 21 seconds, and we can do it again. Let's not do it again. Let's do it with 10,000 rows. So remember, we got 21 seconds, and then for 10,000 rows, after everything's been compiled, and actually everything was compiled in the first place, we're going to do this supposedly 10,000 rows in 4 seconds. Now, the only thing that's disconcerting about the way that I'm running this demo is that I'm running SQL Server on an SSD. So basically, the in-memory things are going to go faster for me anyway, right? So it's not as much of an improvement as you would think, because the in-memory is using SSD, or the not-memory is using SSD. So we had 21 seconds and 4 seconds, and you mean we're going to have to wait for 21 seconds for this to, more than 21 seconds? And I believe this gets about 27 seconds or 28 seconds. So it's not even 2x at this point because we're comparing it to an SSD. Everybody okay? And we will actually then only be able to knock it down to 8 seconds. So now we're doing 2x, even with that compared to an SSD. Not that the SSD is going to be as fast as memory, but okay, we're at 24 seconds now. And remember, we stopped at 21, was it? Or am I trying to cheat? 21. Okay, good. So we should get it to about 30, maybe 35, and it should finish even with the, come on. Oh, good. See, the demo works better if you do it in front of people and it actually slows down by itself. There we go. So we got 2x performance improvement there by saying, see, you don't get 2x, and it does it just to spite me. Okay. And we'll do the 10,000 rows, and you can see we're at least going to get 2x here. And actually, how many SQL statements are we doing in our stored procedures against memory optimized tables? One for the order, one for the order details, because we're doing an insert select with a table variable, and one for updating each row. So 4 at least. And there we go. Okay. So that shows how fast it can go even versus an SSD. Are there any questions? Remember, we're doing this with compiled stored procedures. I didn't stop long enough after I said, are there any questions? And if you used interop, of course, it's not going to go as fast. In other words, if you use them with regular SQL stored procedures, or if you use them with just SQL statements without stored procedures, or if you call them from Entity Framework and don't use compiled stored procedures, it's not going to be as fast. You have to use all the pieces in conjunction with each other. How am I doing now? 20 minutes. Good. Because now I get to tell you about transactions. Just to make sure I got everything. We did this, the query plan thing, compile procedures, we did that. Okay, sorry. And we all talked about all the declarations, including delayed durability. And if you don't specify date format and date first, it defaults to the language's default. And if you don't specify delayed durability, it defaults to the database's default. And you can specify not only parameters, but variables as not null, which you can't do outside. There's the atomic block. And because this system is based on the fact that all transactions will complete, it's possible to have transactions roll back. So you must, or you should, use try-catch to limit the rollback. Or you can limit the rollback by catching the errors on the client side and trying it again. But you're going to have retries in this system. That's what you get for latch and lock free. Okay, and here's the use cases for compiled stored procedures. Interestingly, and I don't know, I have 20 minutes, maybe I can do this. Well, in the books online, there's a new page in the books online called Query Processing for in-memory, for compiled stored procedures, and it lists all the iterators that you can use, or that it can use. And it turns out that, how many iterators do they have in SQL Server? Anybody know? Approximately. Different different operators that you can see in query plans. About 67, right? You can see this in the XML schema for query plans. And so even though they're missing a few. Now, it turns out that on the books online, there's now a list of all the iterators that you can use in compile stored procedures, and except for seek and scan, which they apparently don't think is useful to talk about. And there are about 9 that you can use in compile stored procedures. 4 of them being select, insert, update, and delete. So maybe 9, maybe 11, right? So you can use nested loop joins. There are no other join types. You can use stream aggregates. There are no hash aggregates in this world. And you can use top clauses, you can use sort, and you can use top sort. And I believe the other one is compute scalar. And that's about it, right? That's all it can do. So when it says it's optimized for nested loop joins, well, it better be, that's all you can do. And optimized for aggregation with stream aggregates, that's all you can do. And multi-statement, insert, select, update, and delete. Complex expressions with mathematics in it, although you could do those in CLR as well. And I love this, procedural logic like conditionals and loops. Isn't SQL a set-based language, and we always used to tell people not to do that? So it's optimized for things that you're not supposed to do. The more things that you do that you're not supposed to do, the faster it goes. Okay, compared to the lousy SQL you wrote in the first place, right? People think because things written in a stored procedure, that's enough, right? No, it isn't, right? You have to write SQL like a set-based language. Okay, so again, the code is never auto-recompiled. It consists of table I/O and built-in functions, and there's a limit to the number of built-in functions as well. They support, I believe, and I don't have exact numbers, somewhere around a fourth to a third of the built-in functions in SQL Server. Really, a subset. Right now, remember this is version 1, and remember they could finish column store in version 2. So, and optional DMV information. So, what's the DMV that everybody uses to look at stored procedure performance? Well, there's two, right? sysdm exec query stats and sysdm exec procedure stats, right? Those show the performance. And just don't do it, you're getting behind. Okay, I'm going to do it anyway, right? So if you look at what's in here, and I'm not even going to resolve the SQL statements at this point, the reason why people usually use these for performance is query stats. You get one row for every query in a stored procedure or ad hoc query, and it tells you information that helps you diagnose problems with the query. And never mind the fact that you can resolve the SQL statement, and never mind the fact that it'll tell you a plan handle so you can resolve the query plan and the last execution time and things like that. But you get to see the total worker time, which is the amount of time that my process or my procedure has control of the CPU. That's not the same as clock on the wall time. Total physical reads in pages, that's from disk. Total logical writes, because SQL Server never writes to disk. He writes to buffer pool, and lazy writer writes when he feels like it. But remember, he does write to the transaction log. These are also in pages. Logical reads from the buffer pool in pages. Well, are those useful for memory optimized tables? No, not at all, because we don't work in pages. So those are always going to be 0. And then total CLR time, well, you can't use CLR and in this world, and total elapsed time, clock on the wall time. So basically, they didn't think it was useful for these compiled stored procedures to keep track of this stuff. So by default, you don't even get entries here for the compiled stored procedures. If you really want to get the clock on the wall time versus the CPU time, then what you can do is you can actually turn on, with a system stored procedure, a flag that says, I do want to collect this information, and realize that that will slow the procedure down, and then turn it off when you're done. Everybody okay with that? All right. See, I said I wouldn't go there, but I did anyway. There's no transact SQL debugging, obviously. If you've got to like the transact SQL debugger, this is compiled code, and they're not going to branch it to the C code. Conceivably, if you got the SQL Server symbols, you could debug an assembler. Only Paul Randall likes to do that. And so there's a multi-version concurrency engine. We talked about that. Only one version is valid at a given time, and which one depends on the transaction's begin time. We already talked about elevate to snapshot. And they say read committed is supported for single statements, but I hate to tell them the read committed that's supported for single statements is snapshot, right? They don't show you things that change while your single statement is executing if tried. And otherwise, the statements need isolation level hints, because they do not run at read committed in user transactions. And this uses super optimistic concurrency. Remember when they said that there was optimistic concurrency and pessimistic concurrency? And it was based on the fact that you would take a bunch of data and put it out in a grid on the web, and then when you update that, if you think nobody else has updated it, you just write your changes into memory. And if you think somebody else, that's optimistic concurrency. And if you're pessimistic, then you would actually check the old values to make sure they were right before you wrote over them, right? Or use a timestamp column, right? That was pessimistic concurrency. This is super optimistic concurrency. This is optimistic concurrency even within the same transaction and the same set of statements, basically, that says, we assume that everybody before you is going to commit, and yours is going to commit. And if everybody doesn't commit, then we're in trouble, right? And if you do violate things at the end, then we're in trouble. And so error handling and retry logic are required, but the thing waits for nothing, right? There are no waits in it. Well, actually, there is one place where you can produce a wait, and I'll talk about it. And I have a demo, I believe I posted on the web, that you can do. So snapshot, the only thing you can get with snapshot is a write conflict. I write something that somebody else has written, or I write something that somebody's deleted since the beginning of my transaction. There are no read conflicts in snapshot. Repeatable, and by the way, this is not the snapshot that uses the, the version store in tempdb. This is their own version of snapshot isolation with the new storage engine. Okay, repeatable read. So repeatable read says rows cannot change after you read them. Actually, this would be rows cannot change since the beginning of the transaction, repeatable read, individual rows. But the problem with repeatable read is, although rows that are there cannot change, you can add new rows. And so if you want to prevent people from adding new rows, you go to serializable, which says not only can rows not change, but you can't insert new rows either in the row range that I'm looking for, right? The index range I'm looking for. And so basically, write-write conflicts in any of these isolation levels work like they work in serializable. They cause rollbacks immediately. However, the violations of the isolation level cause rollbacks that happen at commit time. So how many minutes do I have? Oh, 13, okay, great. We'll do a compressed version of this demo. Okay. Just trying to figure out how to do this all in an hour and a half, he said. Well, it'd be nice if you knew where your demos were, come on. Stop talking and just do this. By the way, this is on the web too under a simple version of transactions under Hekaton. I already have the simple database. We'll use the simple database. We'll drop these tables just in case I had them out there from yesterday. And procedures. Okay, which I probably did. And really. And then we're going to create tables. Again, simple table with a non-clustered hash index with memory optimized equals on, and schema and data are going to be persisted. So there's the first one, and we're going to put it for 4 rows. Great. There we go. And select, well, we don't need to select, we got the 4 rows. And we'll do the same thing for table 2, and we'll put it in the same 4 rows. And so let's look at the snapshot isolation level first. Snapshot isolation level, there's really not too much you can do with selects to break it, right? I can do updates will break it, but begin transaction, select from T1 with snapshot. By the way, check for comprehension. Do I need that with snapshot hint all the time? What makes me not need that snapshot hint? Memory optimized elevates a snapshot on the database. Right, if I had that, I don't need that hint. All right, so I'm selecting. You're going to go ahead and update. And by the way, this is perfectly okay with me in this isolation level. So update T1, set C2 equals Fred, where C1 equals, well, other people are finished, equals 1. There we go. Okay, so now I go ahead and commit and everything's okay. In fact, I can change it, select it again, it's still going to get the old value, commit, and it's okay. Let's do repeatable read. So with repeatable read, it says rows do not change after the beginning of the transaction. And by the way, transactions in SQL Server don't begin when you call begin transaction. They begin with the first data access after begin transaction. So anyway, begin transaction, select star from T1 with repeatable read. Great. It actually lets me change a row that I've already read with somebody else's ID. There we go. So we'll change it to Ann. And now at commit time, we roll back. And we roll back because a row has changed since I read it. How did they know the row changed since I read it? When I say commit, they reread all the rows. They keep track of all the rows I've read during the transaction in something called a read set. And when I commit the transaction, they reread them and compare them to the old values. Really, really. And if they've changed, then they roll back the transaction. So they read them twice. Now, if you read the academic white paper, it says, you know, this isn't so bad because the rows will probably be in the L2 cache of the processor and it's fine. And actually, it doesn't slow things down that much. But they will reread rows. Best practices, unless you can figure out a reason why you absolutely need repeatable read, don't use it, right? If you need locking, make up user locks, right? Because this system has no locks. Let's do the same thing with serializable. So in serializable, I can't insert rows. So let's go back, I'm sorry. In repeatable read, I can insert a row, right? So begin transaction, select, and then insert a row. Insert a row is fine, right? Update would cause me to roll back. But insert a row that isn't there, because repeatable read with locking locks rows that are there. It can't lock rows that don't exist, right? So we'll call it 5 and 5 and goodness, Bob, hurry up. There we go. Okay, so insert a row. Insert a row doesn't bother repeatable read at all. And in fact, when I go to commit, it commits just great because I didn't update any rows, remember? That's what repeatable read cares about. Okay, serializable on the other hand, this is a no-no, right? So if I begin transaction and select with serializable, then if I go to insert anywhere, right, because I've selected all the rows, so we'll put in 6 and Mary, 65, that's good enough. Then why did you go and erase it? There. Now, I've inserted a row between the last row and the end of the table. And the way that it knows this, and it rolls back, is that it keeps something called a scan set. So for serializable, it has to keep track of all the selects that it's done so that it can redo the selects at the end when you say commit. And not only does it have to have rows that are there not changed, but there also has to be no fewer or more rows. Everybody okay with that? Good. Those are the 3 isolation levels supported, and that's how they do it. Now it turns out that there's a race condition in here as well. So transactions consist of 3 phases. And the first phase is begin transaction. And the second phase is validation phase. Now the validation phase can take some time, right? Because if you're reading a lot of rows or you're doing a lot of scans that's serializable, that means it has to go do those again. So imagine that I make a bunch of changes and I'm validating those changes, and you come in and begin a transaction. What about the rows that I'm in the midst of validating? Because I'm not sure if those are actually going to take or not, right? I'm not sure if my updates are going to take, or my selects will be wrong. Something might cause me to roll back that transaction. Now we don't care about selects in this case, but we would care about updates and deletes, right? So what happens is if you're validating and I start a transaction, the only way that this could work is that I assume you're going to commit, and I have what's called a transaction dependency on you. And to do this, you actually have to do some fairly heavy-duty stuff, at least with a fast system. So I have an example that gets these that actually runs under serializable and reads 150,000 rows and updates 20 of them, right? So there's a lot of things you have to do to force this race condition. But basically, if I'm in the middle of this and you start over here, I now have a dependency on you. And if this is so long that my transaction is finished before your validation phase is finished, I can't commit my transaction, even if I go through all my validation, until you commit your transaction, because I've assumed that yours is going to commit. And so therefore, this is the only possible place, this race condition, where your transactions will wait. Everybody got that? And by the way, you can see this by running an outrageous thing like I did, with multiple threads all hitting the thing at the same time. And there's an extended event for this particular condition. And you can see it in extended events. I don't believe something exists unless I can see it. Garbage collection can always outrun me so far, and so I've never seen a dusty corner. I almost didn't write about dusty corners because I haven't seen one yet. I did some outrageous things to try and see dusty corners. And then once your validation is finished, you go and the end timestamp, or the begin timestamp, depending on what you're doing, has not a timestamp, but your transaction ID. And so when you're finished doing inserts or updates or deletes, you basically go and replace those transactions IDs with end timestamps. How come? Well, because you can see changes that you've made, just like a real transactional system, regular transactional system. Real is what I'm used to, right? Are we done? Yeah, there's the scan set, there's the write set, and we have a couple more things. There's speculative reads, right? You're validating and I'm reading, right? And you can also have speculative deletes, where since you deleted stuff and you're validating, I assume your deletes go forward too, right? Okay, and garbage collection, I think I'll just soft pedal garbage collection. There's 2 types. One where it garbage collects the individual rows, the other one where it actually compresses the checkpoint files. Because obviously, if you have these huge checkpoint files and somebody comes in and says, checkpoint, 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 you're wasting them. So what basically happens is they look and see if checkpoint files are, adjacent ones, are less than 50% each full, and they'll merge them together. This is an automatic process, but you can actually cause it to do that if you know it's supposed to do that and it hasn't started yet. But there are limits. And remember, this is version 1. These are just some of the limits. There's actually 9 different tables in the books online, and I can actually post all the URLs to them if you want. Most of them are things that you cannot do, but they've actually tried to make them a bunch of things that you can do, so to phrase them in a positive way. But let's see, one of the more interesting things is, oh, you can't do an outer join inside of a compile procedure, but you certainly can do one with regular SQL and a memory optimized table. No constraints we've already talked about. The bin2 collations we've already talked about. No blob data types, right? That only makes sense. Truncate table is unsupported. How come? Truncate table works by snipping the pointer to the first row. If there's no pointer to the first row, then you can't do it. And order by and comparison, where clauses in compile procedures actually have to have bin2 collations. So if you don't have a bin2 collation on everything, remember your collate, or sorry, memorize your collate clause well. You do realize you can use collate on variables. You can use it in a where clause. You can use it in an order by clause. So be careful. And then limits on the transaction isolation level, he said, as he trips over the thing. So there's only one more thing to say, and we can go over all these differences between them, account for errors. No parallelism in query referencing a memory optimized table. It's supposed to be an OLTP system. You don't need parallelism in OLTP. Optimized for hint is useful. Design changes because of limitations right now. And a smaller function library and surface area. There was just a guy that rewrote rtrim. And you take his rtrim code and you have to put it in every procedure. Management differences, no index rebuilds, but you can use the statistics. And what I really want to get to, does anybody have a problem with these? Must have sufficient memory, I've said that. Limit of 256 gig, that's fine. Is how do you, and instrumentation, we have a bunch, right? We have DMVs, a whole ton of DMVs. I'll just give you the list of DMVs so you can run them, and perfmon counters and metadata. But how do you decide which part to migrate? Remember, the fourth pillar was that it's built into SQL Server, and so you can migrate these in little dribs and drabs. There's a couple of different ways. One is the fact that they actually have a data management warehouse set of counters that will actually go and figure out for you the best ones to migrate. And so you use the data collector. If you haven't used the data collector before, you have to set up the data collector, and then you can install these two. Basically, this is the stored procedure usage analysis and the table usage analysis. And as long as you're using SSMS version 2014, you can run these against lower version databases. So this works just fine against that. And basically, you run these, they collect data, and then this is the hard part, at least to me. You have to know where to look for this report. It's under where you put the management data warehouse. It's not under data collection like I thought it would be. And you right-click and say, I would like to see the reports of the management data warehouse, and I want the transaction performance overview. So basically, for tables, it tells you which are the best tables to migrate based on how complicated it is and how much gain you will get. So the more complicated with the most gain are over here. Sorry, with this little bitty font. There we go. And the highest gain ones are on the top and the lowest gain ones are on the bottom. And they do this for every table. You can imagine that they do this also for every stored procedure, right? It's the same chart. And so I'd scroll back and forth with this big font. People would go, what's that chart do? Okay, anyway. Now, you can do this as well just to see that there is going to be some kind of work involved at this version of SQL Server. And these are the table and stored procedure advisors. And basically, you can right-click on a table in SSMS 2014, and there's something called the Memory Optimization Advisor, which is what I wouldn't think it would be called, but I'm not sure what I would call it. And basically, it says, we're going to analyze your DDL for your table to see if it's a good candidate for, for changing it. Where's the next button? Oh, BEP. There we go. So don't run with the hideously large font, right? And there you go. So it's telling you all the things about this table you're going to have to change to make it a memory optimized table. By the way, most of these that I can see are foreign keys that you have to take off. That's the big one I would like to see put in next. And there's no user-defined data types. If you use UDDTs, then you can't use them. Also, if you use UDTs, you can't use them. Remember, UDDTs are alias types. So if you use alias types, you can't. They don't support those either. Same thing for a stored procedure. And again, I dare you to find a stored procedure in any sample database. Because in sample databases, they're always trying to illustrate the newest, coolest things. So find a stored procedure in a sample database that actually converts. Let's see. We'll do the, salesperson. Oh, those are tables, aren't they? Yeah, they are. Come on, Bob. So here's my, no, maybe they aren't. Programmability, stored procedures. Get bill of materials. Oh, I can almost bet you this won't. And this is the native compilation advisor for stored procedures. And then you hit, when you've made the dialog big enough, next. And then it validates and says one or more transact SQL elements exist that are supported, unsupported. And you click next and it tells you what you can't do, right? So in this case, you can't do one part names, you can't set no count on, because no count on is on by default, by the way. And you can't do CTEs. and certainly not recursive CTEs. So make a bunch of noise. Okay, so anyway, that's the feature in a nutshell, and it's actually only 2 after. Do I have any questions? Basically, remember the story. The story is that they have decided in SQL Server that multiple storage engines within the same exe is a good idea. In the last version, they put in a special storage engine for OLAP. In this version, they put in a special storage engine for OLTP. SQL Server now has 3 storage engines, right? And in 2012, there were some limitations to the OLAP one, which they fixed in 2014. In 2014, there's some limitations to the OLTP one, which they will fix in the next version or the version after that. If you use this feature in earnest and have opinions on what should be fixed first or what limitations should be taken away first, you can write to the SQL Server team and tell them. Do I have any questions? No? Yes, sir.
Does it scale for a cluster server somehow? I mean, I don't see how without further communication.
So what they found out the biggest problem was with scaling was the lock table. There is only one lock table, and so without a lock table, it scales quite nicely. It doesn't scale past 60 CPUs though right now. Right, that's a limitation, right? You know, that you won't get a goodness after 60 CPUs. And the second biggest bottleneck is the transaction log. And so if you wanted to scale past the limit of the transaction log, you can use that delayed durability and take your chances. Remember, we've got used to the term eventual consistency. So now we can get used to the term delayed durability. Any other questions?
You mentioned that if you're doing interop between memory optimized and normal table.
Yes, sir.
The performance hit.
Yes, sir.
So is that worse than a normal table to table join?
Oh, no, it's not
Or
worse.
is it better?
It's the fact that in that special query processor, they've gotten rid of 99% of the instructions, and you're putting those back, right? It's just being used by the regular query processor. And in that case, though, you can do everything that compile procedures cannot do, except truncate table.
And does that have any performance improvement over a regular table?
Oh, absolutely. So imagine that for memory optimized table, there's a performance improvement of X. And then for stored procedures, there's compiled ones. There's a performance improvement of Y on top of it. And then if you do a lot of transaction processing where locks are a problem, that's why the silliest example to do in the world is to do a bunch of inserts as fast as you can. That's not real, right? You're not even measuring that last possible improvement, which is there's no lock table, right? So do your regular workload against it. Try with 1 or maybe 2, right? These you can get that for nothing. And then 3 would be to actually put on the compile procedures. Any other questions? Okay, well, thank you very much. I now declare it lunch. Thank you for coming. You know, knows that it's out there, and then it returns immediately and says it's been committed. And so you have the potential with that delayed durability to, you know, lose data if SQL Server crashes or in odd race conditions that happen at shutdown time. So do realize, though, that'll make it run way faster as well. The one that I've seen with the many, many inserts in a row, which is the one everybody likes to do and I refuse to, will actually run 20 times faster if you have delayed durability on. So you can tell that the transaction log is the big bottleneck. Okay, so we need a demo. So I'm trying to cut down on demos because I do have way too many of them. And so the demo that I'd like to do is actually one that's a complete end-to-end demo that you can get. This is the public demo that they've put out for everybody. And this uses AdventureWorks, of course. And so the first thing it does, if you've seen this demo, whoops, sorry. I actually have a bunch of my own demos where we start from scratch, but this sort of has one of everything. So we'll see what we get. Okay. And it's this one right here. So go. By the way, I'm going to give you all of the demos as if I did them all anyway that we have from the 5-hour version. So basically in AdventureWorks 2012, it's going to check to see if you have an in-memory file group, which I don't right now. And if you don't, then it's going to add an in-memory file group. So it's going to add one called AdventureWorks 2012 mod, and it's going to add a file name to that file group. And you'll see that it'll produce something that looks exactly like a file stream file group. Sorry, file stream file group. There we go. And so if I go up to my T drive, we should see that the in-memory data, and if I wait long enough, is going to be stored right here. And notice this is a file stream file group. Sorry, let me go back and put the zoom it on. This thing looks so hideously large in this font that it's like I forgot about zoom it. Good. So anyway, if we go back to the file system, there we go. And we can see that under data, it's over here. And basically, there's the file stream concept with the multiple GUIDs, first one, and then the first one under the first one. And right now, it's empty. This is going to be filled in later on. Yes, ma'am? No? Okay. This is going to be filled in later on with a set of checkpoint files. Checkpoint files are basically pairs of files, and the big one is where they store the data. It's a 128 megabyte file, and there's 8 of these pairs. So basically doing this is eventually going to allocate a gigabyte of space just to put a memory optimized file group on there. And then the little ones are actually delta files, which is where they store the key values of the rows that have been deleted. And we'll see that this is necessary for the multi-version concurrency control. So usually if you wait long enough, these appear, but we'll forgo them for now. We'll see them later on. So notice that at this point, you can alter the database to set memory optimized elevate to snapshot, which is easy if you don't want to have a hint on every query that runs in read committed. And then a couple of other set options, which I'm not sure that we need because I did it yesterday without them, but we'll go. Sorry, that's not a feature itself, but that's sort of an implementation detail, but that's a big detail. That means you can change part of your application without changing it all. I'm not anybody is free to contradict me if they want. I'm not an expert in this, but supposedly Oracle times 10 is a separate in-memory database, and you must convert to times 10. You're either in there or you're not in there. With this, you can be half and half. So the components of this are the XTP storage engine, and the XTP storage engine does all of these different things. It manages storage. It manages 2 types of index. Notice we have hash index and range index. And the range index is actually based on something called the BW tree, which is a lock and latch tree version of the B tree. Transactional operations are handled by the storage engine. They have a multi-version concurrency engine, and checkpoint is different for these guys. Recovery is different for these guys. And the only thing that's about the same is high availability. So in-memory tables, to me, when I first heard about it, sounds like the system crashed, the table is gone, right? These in-memory tables are transactional, point-in-time recoverable, and persistent. So when they actually write the in-memory table, they will also write to the transaction log. And the transaction log turns out to be the biggest bottleneck at this point because the transaction log is a synchronous write. So they actually have something for that if you want to be risky. But what they also do, what they also do is persist things in continuous checkpoints. So basically, they write continuous checkpoints to files in memory that actually live in file streams, if you remember file streams from 2008. And so they can recover everything with point-in-time recovery. They can also ship those over across to a high availability replica and do high availability with those as well. The things that do not persist in a high availability failover are the things like memory optimized tables that aren't persistent and memory optimized table variables. But if you call a table persistent in the DDL, it will persist. The XTP compiler actually compiles stored procedures into code, and it's assembler code. They use an intermediate format that's XML, but they take table definition and stored procedure definition, and they compile it into an XML format, and they compile that into C, and they compile that into assembler. And I sort of spoke before myself here. They also do this with table definitions. So if you have an in-memory table, it actually produces a DLL as well. And this DLL contains the I/O routines for this table for the new query processor, for the new query execution engine. So native access routines for in-memory objects. And then finally, integration with the rest of SQL Server resources. So integration with transact SQL statements, ordinary transact SQL statements that are not compiled, and a library of functions for compiled procedure, because the compiled procedure has its own function library, or through interop, it can actually use SQL Server's library of functions. There's limitations. So to get started, because most people like to see it, you must have a 64-bit version of SQL Server. It must support a machine instruction called compare and swap. And most 64-bit servers support compare and swap. I think there's one virtual machine vendor that doesn't support it unless you turn it on. So if you're having trouble with it, you're either running the 32-bit edition or you have one of the few 64-bit processors in the world that don't support compare and swap. And compare and swap is one of the ways that they have B-tree-like indexes that are latch and lock free. You need a database with a file group for memory optimized data. It's not good enough to have a file stream file group. You have to have a file group for memory optimized data. It will produce, though, a file stream-like format. And file group can have multiple containers. And the reason why you might want to have multiple containers for your file group is that when SQL Server comes back up again, it actually loads all the memory optimized tables out to memory. And it will parallelize that load. So if you have multiple file groups, then you can load it in parallel to load faster. So the database isn't available until everything gets loaded out into memory. And actually, it is quite fast that you would think, oh, that'll take a long time to come up. Doesn't really. And again, the checkpoint data is stored in file streams. And you want to carefully consider the collation of your database. Because one of the limitations right now is that if you're doing comparisons in compile stored procedures, or if you're writing indexes over character-based columns, you must use a bin2 collation. And if you haven't used bin2 collation, it's a collation based on the Unicode code point number. And what that means in terms of reality is the uppercase characters will all sort before the lowercase characters. So that's the only way they can do a where clause in a compile procedure. Remember, you can use SQL interop, like I said on the last slide. So carefully consider the collation of your database. You can also, for your database, consider memory optimized elevate to snapshot. So the memory optimized tables support 3 transaction isolation levels. None of them are read committed. So the lowest isolation level they support is snapshot. The one after that is repeatable read, and the one after that is serializable. And we'll see if we have time how each of these works. So normally, of course, SQL Server is going to run it read committed. And at first they thought, well, that's okay. We'll make everyone put a snapshot hint on every memory optimized table that they execute in SQL. And it's like, nah, maybe that's not a good idea. So you can run it read committed. Even in a transaction, if you have this turned on, it'll just escalate everything to snapshot. And actually, you'll see why we need snapshot later on. And then you can carefully consider something called delayed durability. So that's another feature in 2014. You can use it outside of Hekaton tables as well. Here's how it works. Remember now we have the transaction log as the bottleneck. So what happens with the transaction log is usually you commit the transaction, they write to the transaction log, and then they get back to you with the information that it's been written. And you sit and wait until they get back to you with the information. So what delayed durability does, and you can do this if you'd like, is you say commit, and it goes to write to the transaction log and starts to see it, find it. Good morning. So first talk of the day, and I'm going to talk about SQL Server 2014 in-memory OLTP and why is it being upset at me. There, because it's not in memory, that's why. Okay. So this is me, and I got to stop it coming down like that, but this is what I do. This is the company I work with, a company named SQL Skills. If you know SQL Skills, you know Kimberly Tripp or Paul Randall. Probably not me, maybe not. There's their website and blog. And I've written a bunch of stuff on 2014, including how to make one transaction depend upon the other and have them all roll back in Hekaton. Email and Twitter. And there's some stuff I've done. I wish it didn't come out one line at a time. And 2012, I actually wrote a chapter in Kaylin Delaney's book on special indexes, which is interesting. Which is interesting to me, I'm sorry. Spatial indexes, full text search indexes, XML indexes, semantic search indexes. Okay, let's go. So this talk is about in-memory online transaction processing, which is also known as Hekaton, which also has another code name that I'll talk about. And we'll be talking about these things. So there's 2 general categories of applications that live in the database world. One of the main ones is called OLTP. And in OLTP apps, you actually read very few rows at a time. You're usually reading a row about me or about somebody and displaying all the information on the screen. And you usually read many or all of the columns in every row. And in OLAP applications, you usually read a lot of rows. You're doing reporting, or you're doing cubing, or you're doing some kind of analysis. And you read very few columns in every row. Fact tables are huge, 25 columns, and you need maybe 2 of them for any one query. And so in SQL Server 2012, they introduced technology to speed up OLAP apps. And they thought, well, really, though, the majority of our users are OLTP. And so in 2014, they introduced technology to speed up OLTP apps. And this is now called, marketing people got to it, and it's called in-memory OLTP. It was actually codenamed Hekaton, and Hekaton means 100 times. I don't believe they've got an actual user to go 100 times faster yet, but the premise was that the goal was 100 times faster. So they did things like get rid of 99% of the instructions that you would execute if you're running in a compiled stored procedure. And they invented an entire other engine for this thing. It's also known as XTP, Extreme Transaction Processing. And that sounds more markety than anything else. But if you're actually looking to diagnose things, if I go into Control Panel and then go to Administrative Tools and go to, goodness, where is it? Where's perfmon? Perfmon just looks funny at this resolution, that's all. And I go and add a perfmon counter. Do realize that outside of the SQL Server set of counters, there appears the counters for XTP. So do realize that XTP will be useful to you. Or if you want to go into SQL Server Management Studio and look for extended events because you want to trace something that's not working the way you think it is, and you go and make an extended event session, you'll see a bunch of stuff for XTP, and they're all called XTP. So, or most of them are called XTP. So extended event session, new session, call it Z, come on, there. And I want to look at the debug channel. Remember that if you ever want to look at any internals in extended events, you want the debug channel, because that's the one that has all the internal things. And then look for XTP, and you've got a ton of things that you can look at. So XTP is not just a marketing buzzword, it's actually what things are categorized as in the diagnostic tools. Sorry, I do mostly diagnosis. So those are the 3 names for it. So really, this feature consists of 4 main features. Actually, 3 of them are features. One is sort of a good thing about it, an implementation detail. And the first feature is there's a brand new storage engine. This guy runs in his own storage engine. They're not using the regular storage engine, they're using his own. These rows don't live in pages, and they don't live in extents and anything like that. They're just sort of disembodied rows that live in memory. And this is memory optimized tables. So if you have a memory optimized tables, basically, memory optimized tables are based on linked lists and pointers, not, not pages and extents. And then we have the compile store procedures. Compile store procedures at this point in history, and do realize it is a version 1 feature, they're going to add things. At this point in history, can only access memory optimized tables. So if you want to join with a memory optimized table and a non-memory optimized table, you can't use these. And these actually have not only a separate procedure compiler, so you can compile store procedures into assembler, like big deal, right? But they do have a separate query processor, and it works differently than the way the regular query processor works, and I'll show you a summary of how that works. And then finally, it's lock and latch free. So they have tables that are lock and latch free, they have transactions that are lock and latch free, and they actually have indexes that are lock and latch free. And how do they do lock and latch free? That seems kind of strange. And what they do is they assume that every transaction will commit. And so if things don't commit, you don't wait, but you are eventually going to roll back, and we'll see how that works. And then finally, the big deal is, apparently it's fine to go out and build another database for something. I was reading an article that somebody had spoken to Michael Stonebreaker, the database guru, and he said that we were going to separate databases for separate things, and he mentioned an OLAP column store type database, an in-memory database for OLTP, and array-based database for for analysis, like SAS has an array-based database. And the interesting thing is he thought these were all supposed to be different databases. The SQL Server folks think this is all supposed to be built into SQL Server. So a lot of the work they did was actually to integrate it so it shows up as regular tables, the metadata shows up as sys tables, and you can interact between these tables and tables that aren't memory optimized without much problem or without a lot of overhead. So the fact that they're built into SQL Server is an interesting feature as well. like I said, that's not a feature, an implementation